Hi, welcome to the second lesson on number properties. Today's lesson is very important. It deals with that most crucial topic, divisibility. We discuss when an integer is divisible by another integer. Divisibility leads to the concepts of quotient and remainder. Then we move on to prime factorization. We introduce what prime numbers are. Prime numbers are essentially the building blocks of all integers. Every integer contains some prime within it. We introduce the notions of factors, highest common factors, multiples, least common multiples, and their relationship with each other. We look at several problems that use these concepts in many clever ways. So let's begin with integer division. What does it mean for an integer to be divisible by another number? We say that 4 is divisible by 2, and we say that 5 is not divisible by 2. What does this mean? 4 is divisible by 2 because it can be expressed as 2 times another integer, in this case 2. 5 is not divisible by 2 because it cannot be expressed as 2 times any integer. I know it's 2 times 2.5, but 2.5 is not an integer. Here we are limiting ourselves to integer division. All numbers involved are integers. So, divisibility is easy. 4 is divisible by 2, 5 is not. So what happens in the case of 5? Well, in the case of 5, 2 goes into 5 2 times. That is, we get 2 times 2 is 4, and then there's 1 left over. 2 does not go into that 1. So we can write plus 1. 5 is equal to 2 times 2 plus 1. This 2 and this 1 are important concepts. This 2 is called the quotient, and this 1 is called the remainder. So the complete statement is when 5 is divided by 2, we get a quotient of 2 and a remainder of 1. As we can see, given the quotient and the remainder, we can build back the original number. Some quick examples. Find the quotient and remainder when 10 is divided by 6. So 10 divided by 6. The way we write it is 10 divided by 6. It's equal to, well, 6 goes into 10 once. So I get 6 into 1, and what's left over? 4 is left over, so that's the remainder. The quotient is 1, and the remainder is 4. 5 divided by 3. 3 goes into 5 once, and the remainder is 2. 3 is used up, and there's 2 left to make 5. Again, the quotient is 1, and the remainder is 2. 8 divided by 2. 2 goes into 8 4 times, and what's left? Well, there's nothing left. 2 times 4 is 8. So we're left with 0. Here 4 is the quotient, and 0 is the remainder. We can also say that 2 divides 8. Why? Because it goes into 8 perfectly. There is no remainder. So we use the word divides when the remainder is 0. And the last one, 3 divided by 7. That's interesting. That deserves a box of its own. 3 divided by 7. So how many times does 7 go into 3? Well, 7 can't go into 3. So it's 7 times 0. And what's left? All of 3 is left because 7 didn't go into 3 at all. So the remainder is 3. We have a quotient of 0 and a remainder of 3. The last example is very important. Most people wouldn't know how to tackle it because the magic number 0 has shown up. It's actually the easiest division to perform. You haven't done anything. Since 3 is less than 7, 7 can't go in, and what are you left with? You're left with 3. So let's deal with 0, which is a big issue. Is 0 divisible by 3? So what's our definition of divisible? Divisible means the remainder is 0. Divisible means that the first number goes properly into the second number. That is, the divisor goes properly into the dividend. And there is no remainder. So is 0 divisible by 3? So let's see. 0 divisible by 3. So how many times does 3 go into 0? Well, can't go any more times than 0. So 3 into 0 plus what's left over? Well, 0 is left over because you had 0 to start with. You can't have suddenly something positive left over. So what is the remainder? The remainder is 0. So by our definition, divisible means the remainder is 0. So 0 is divisible by 3. We got a remainder of 0. So the answer is a resounding yes. How about by 2? Well, of course it is. 0 is divisible by 2. 2 by 99. Yeah, I guess it is. 99 times 0 plus 0. The remainder is still 0. So 0 is divisible by every positive number. Is 3 divisible by 0? Is 3 divisible by 0? What does this question mean? So what does divisible mean in general? What does it actually mean to say, what is 5 divided by 2? Well, 5 divided by 2 could be expressed as, I have 5 things and I want to give it equally to 2 people. How many do each get? So when I have 5 things and I want to give it equally to 2 people, then each would get 2 and I'd be left with 1. So the quotient is what each person will get, and what I'm left with is the remainder. That's why it's called remainder. That is the basic understanding of divisibility that one should always have at the back of our mind. Going back, what does 0 divided by 3 mean? Well, 0 divided by 3 means I have 0 things and I want to give it equally to 3 people. Can I? Of course I can. I just give none to each. I give 0 to each. And I've given my 0 things equally to 3 people. And what am I left with? I'm left with 0. So I have managed to give 0 equally to 3 people, which means 0 is divisible by 3. If I could not give 0 equally to 3 people, then 0 would not be divisible by 3. The next bizarre question. 3 divided by 0. What does this mean? It means I have 3 things and I want to give it equally to 0 people. Well, there are no people to give it to. So what can I do? I can't do anything. I cannot say at the end of it that I have given 3 equally to 0 people, because 0 people means no people. So colloquially, this question doesn't make sense. It is not possible to give equally to 0 people. What could be your answer? Yeah, I gave equally to 0 people. Then I'd ask, how many did you give to those 0 people? And you wouldn't have an answer. So this is not an allowed operation mathematically. We cannot divide by 0. So is 3 divided by 0? Not answerable. This question does not make sense. How about 0 divided by 0? Again, division by 0 not allowed, so cannot answer this question. So remember, we'll always keep that colloquial understanding of divisibility at the back of our minds. It really helps formulate our thoughts clearly. So let's look at some properties of the remainder, because the remainder is the thing that decides whether a number is divisible or not. If the remainder is 0, it is, otherwise it's not. So what do I mean by remainder of a sum? I mean that if n is divided by, say, q with a remainder of r, and m is divided by q with a remainder of s, these are the remainders, then when n plus m is divided by q, the remainder will be r plus s. The remainders add just as the dividends add. When n minus m is divided by q, the remainder will be r minus s. When n times m is divided by q, the remainder will be r times s. Will it? Well, not quite. In each of these cases, the remainder will be r plus s or r minus s or rs, but it will have to be further divided by q to actually bring the remainder to the range 0 to q minus 1. So, further divide to find remainder in the range 0 to q minus 1. We look at some examples to make sense of this. So basically, if I add two numbers, I can add the remainders and then do the division by q on the remainders and get the final remainder. Similarly, if I multiply two numbers, I can multiply their remainders and then do the division by q on the remainders to get the final remainder. So it's a quick way to cut down your work. So here are some examples. The remainder when y is divided by 11 is 8. What is the remainder when y plus 2 is divided by 11? Y divided by 11, remainder 8. And in question A, I'm asking for y plus 2. So let's find out what the remainder is when 2 is divided by 11. So when 2 is divided by 11, the remainder is 2. Because 11 is greater than 2, the quotient will be 0 and the remainder will be 2. Now I'm adding the numbers. So when y plus 2 is divided by 11, the remainder will be the sum of the remainders. So it will be 8 plus 2 equal to 10. Since 10 is a valid remainder when dividing by 11, I don't have to cut it down further. The remainder is 10. How about y minus 5? To do y minus 5, I need to find out what, when 5 is divided by 11, what's the remainder? Well, it's 5 because 5 is less than 11. So when y minus 5 is divided by 11, the remainder will be the difference of the remainders. So it will be 8 minus 5 equal to 3. So we have the remainder when y minus 5 is divided by 11. When 3y is divided by 11. So I need to do 3y. So I need to find out when 3 is divided by 11. That remainder is 3. So 3y is divided by 11. That remainder will be 8 times 3 equal to 24. But this is not a remainder when divided by 11. So I need to divide it further. So that's 24 divided by 11. And that gives me a remainder of 2. So the final answer when 3y is divided by 11, a remainder of 2. The last question, when 2y plus 1 is divided by 11. So when 2y plus 1 is divided by 11, let's do this in steps. We know that y gives a remainder of 8. We know that 2 gives a remainder of 2. So 2y will give a remainder of 2 times 8 equal to 16, which I need to further divide by 11 to get a remainder of 5. So 2y plus 1 will give a remainder of 5 plus 1 equal to 6. Of course, I've used the fact that 1 gives a remainder of 1 when divided by 11. So the final answer is 6. Here's one more. The remainder when m is divided by 5 is 2. So m divided by 5, remainder 2. N is divided by 5, the remainder is 3. What is the remainder when 4m plus 3n is divided by 5? So putting together all those rules, I know that 4 when divided by 5 will give a remainder of 4 and 3 when divided by 5 will give a remainder of 3. So I just keep those facts at the back of my mind. So 4m plus 3n would give a remainder of 4 into 2 plus 3 into 3. This is the remainder of m, the remainder of n. So I've used the rule for multiplication and the rule for addition in one shot. And this number is 8 plus 9 equal to 17. So now I've got to cut 17 down to size. So 17 divided by 5 is 5 into 3 plus 2. So the final remainder is 2. Here's a typical statement about remainders. M divided by 13 gives a remainder of 4. Can you give me some possible values of m? So m must be 13 into some integer plus 4. So let's see. 13 into 1 plus 4 is 17. Or m could be 13 into 2 plus 4. That's 13 more. 30. Or 13 into 3 plus 4. That's 13 more again. 43. That's a nice pattern. I find the first one and then I keep adding 13. Because adding 13 will only change the quotient. It will not change the remainder. Because those new 13 can be given 1 each to the 13 people. So the quotient goes up by 1. Each of those people get 1 more, but the remainder is the same. So my first choice of M is 17. Can I get a better choice? Yeah. I could give none to all the people. The quotient could be 0 and leave a remainder of 4, and that's 4. That's the best choice. My best choice for M is the remainder 4. So if M is 4, then 4 divided by 13 gives a remainder of 4 because the quotient is 0. So here's your big hint. Always take M to be the remainder itself. If they say M divided by 13 has a remainder of 4, then you can take M to be 4 and work out your question. Of course, be careful that the question allows you to take M equal to 4. Suppose they say M is a 2-digit number, then you can't take M equal to 4. Then you'll be forced to take M equal to 17. Suppose they say M is a number greater than 50, then you can't take any of these. You'll have to take the next one, 43 plus 13 equal to 56. Then you'd be well advised to take 56 as M and not any of these values. But in general, if the statement is just M divided by 13 gives a remainder of 4, then taking M as 4 is your best bet. The number 3 divides X with a quotient of Y and a remainder of 2. So X divided by 3 gives me a quotient of Y. So that's 3 into Y plus 2. So X divided by 3 is equal to 3Y plus 2. That means X is equal to 3Y plus 2. The number 3 divides Y with a quotient of 2 and a remainder of 1. So the number 3 divides Y. So Y divided by 3 gives a quotient of 2 and a remainder of 1. This means Y is equal to 3 divided by 2 plus 1. So we have Y. We have Y is 7. Once I know Y is 7, I plug that value of Y into the equation for X and I get X. So X must be 3 into 7 plus 2. That's 23. And we're done. The answer is D. A teacher was trying to arrange the students of her class in rows with an equal number of students in each row. First, she tried to arrange 4 students in a row. So that means the total number of students, let's call them N, is being divided by 4 to get the number of rows. Each row has 4 students. So when I divide N by 4, I get the number of rows. So N divided by 4 is number of rows. Next, she tried to arrange 6 students in a row. So she divided N by 6 to get the new number of rows and maybe a remainder. In each case, she was left with 1 extra student. What does that mean? That means she got some students sitting in rows and then she was left with 1 extra student. She was left with a remainder of 1. So what do we know? We know that N divided by 4 gave a remainder of 1. We also know that N divided by 6 gave a remainder of 1. However, when she tried to arrange 7 students in a row, she was not left with any extra student. What does that mean? That means the number of students is divisible by 7. She did not get a remainder. N divided by 7 gave a remainder of 0. That means 7 divides N. What is the minimum number of students in the class? So let's start with this information. 7 divides N. So what are the possible values of N? Well, the first possible value of N is 0. But you can't have 0 students in the class. And of course, if I divide 0 by 4, I'm not going to get a remainder of 1, which is what they've told us. So 0 is out. Next value of N is 7. Looking at all the multiples of 7, because 7 divides N. I've concluded that. 7. Can 7 students be there? I need to check the information. 7 divided by 4, the remainder is 3. So it can't be 7. Let's try 14. 14 divided by 4, the remainder is 2. So it can't be 14. 21. 21 divided by 4, the remainder is 1. Yes. So the part about slotting them into rows of 4 works. How about divided by 6? Because she also slotted them into rows of 6 and got a remainder of 1. Is 21 divided by 6 giving a remainder of 1? 21 divided by 6 gives me a remainder of 3. 18 plus 3, the remainder is 3. So 21 doesn't work. Let's try 28. Well, 4 divides 28, so it's not going to work because the remainder is not 1. How about 35? Does 4 divide 35? No, it doesn't. The remainder is 3. 32 is a multiple of 4 plus a remainder of 3. How about 42? If 42, the remainder will be 2. 4 times 10 plus 2. How about 49? Well, 4 does give a remainder of 1 when 49 is divided by 4 because 4 times 12 is 48 and a remainder of 1. How about 6? Does 6 give a remainder of 1 with 49? Yes, it does. 6 8s are 48 and a remainder of 1, 49. So, 49 is the first number which satisfies all three properties, and they want the minimum number of students. So 49 is the minimum number of students. The remainder when the positive integer n is divided by 7 is x. Let's write this down. N divided by 7 gives me a remainder of x. The remainder when n is divided by 14, the same number n is divided by 14, the remainder is x plus 7. I get a remainder that is 7 more. Which of the following could n equal? Fine, so I just need to check the information. I divide each of them by 7 and see what happens. So 45 divided by 7, 7 6 are 42, the remainder of 3. 6 plus 3. So x is equal to 3. Then I need to divide 45 by 14. That's equal to 7 into 3, 14 into 3, that's 42 plus 3. So the remainder is equal to 3. The remainder is not equal to x plus 7. I needed a remainder of 3 plus 7. So 45 is not my answer. Let's try 53. When I divide it by 7, 7 7s are 49 and a remainder of 4. So x is equal to 4. Let's divide 53 by 14. That's 14 into 3, 42 and a remainder of 11. So the remainders are different. The remainder is 4 in this case and 11 in this case. And 11 is x plus 7. 11 is 4 plus 7. So 53 is my answer. When 53 is divided by 7, I get a remainder of 4. When 53 is divided by 14, I get a remainder of 11. And the two remainders differ by 7, which is what we wanted. 53 is my answer. Let's move on to those famous divisibility rules. Divisibility by 2, 3, 5, 9, 8, and so on. We're going to quickly prove all these rules to show you how easy they actually are. First, we're going to correct the spelling of divisibility. We forgot an I. When a number is divisible by 2, we say it is even. If it is not divisible by 2, we say it is odd. What are the remainders when I divide by 2? Well, the remainders when I divide by 2 are either 0 or 1. So the divisibility rules say the following. A number is divisible by 2 if it ends in 0, 2, 4, 6 or 8. What do I mean by it ends in? I mean the units places 0, 2, 4, 6 or 8. That's a strange rule. Let's see a number. Let's say 246. Is this divisible by 2? Yes, it is. It's 123. Remainder 0. Let's see a number like 30103. Is it divisible by 2? The last digit is 3. So the answer should be no, it's not divisible by 2. Let's quickly divide it by 2. I get 15051 and a remainder 1. So I get a remainder of 1 and it's clearly not divisible by 2. So the numbers that are divisible by 2 are called the even numbers. The numbers that are not divisible by 2 are called the odd numbers. What's special about the even numbers? They give a remainder of 0 when they are divided by 2. What's special about the odd numbers? They give a remainder of 1 when divided by 2. Remember, 0 is divisible by every number. Therefore, 0 is divisible by 2. Therefore, 0 is even. Okay, let's prove this rule. So I take any number. Let's say 346. It's ending in 6, so it should be divisible by 2. And I'll take another number, 347. It's ending in 7, so it should not be divisible by 2. Now remember that the number 346, as we saw in the previous lesson, is actually the number 300 plus 40 plus 6. And the number 347 is the number 300 plus 40 plus 7. If I was to divide 346 by 2, I can divide 300 by 2, 40 by 2 and 6 by 2. Check all the remainders, clump them together and then divide the remainders by 2. All I'm doing is I'm distributing this number 346 among 2 people, gathering all the remainders up and then distributing the remainders till I have nothing left to distribute. So when I divide 300 by 2, of course I can do it. When I divide 40 by 2, of course I can do it. And it's just the 6 that I'm worried about, but in this case I can divide it by 2. Here again, 300 divided by 2 I can do it, 40 divided by 2 I can do it. And the 7 I cannot do, I get a remainder of 1. So what's the big deal? The big deal here is that having broken up the number into hundreds, tens and ones, I can always distribute the hundreds because 100 is divisible by 2. Since 100 is divisible by 2, so will be 200, 300, 400, 500, 600, 700 and so on. They'll all be divisible by 2. 10 is divisible by 2. So if 10 is divisible by 2, so is 20, 30, 40, 50, 60, 70, 80. So similarly, 1000 is divisible by 2, 10,000 is divisible by 2 and all powers of 10 are divisible by 2. 10 raised to n is divisible by 2. If n is greater than equal to 1, that is 10 onwards. So those parts of the numbers are all divisible by 2. So they are taken care of. I've given them equally to 2 people. The only thing left to give equally to 2 people is the units place. It's just this part of the number that needs to be divided by 2. The rest can be always. So this part of the number actually decides whether the whole number is divisible by 2 or not. When is the units place divisible by 2? Well, the units place is divisible by 2 if the numbers are 0, 2, 4, 6 or 8. And it's not divisible by 2 if the numbers are 1, 3, 5, 7, 9. It's only the units place that decides, and that basically is the proof. A, B, C, D, E are 5 consecutive integers in increasing order of size. They're 5 consecutive integers. That means they follow each other, like 2, 3, 4, 5, 6 or 1, 2, 3, 4, 5. Which of the following expressions is not odd? Okay. So these are the odds and evens question. Let's look at some rules for odds and evens. So when I add 2 numbers, is the sum odd or even? Depending on what the original numbers are. So if I add an odd number and an odd number, will the sum be odd or even? The first number is odd. That means when I divide it by 2, the remainder is 1. The second number is odd, so it also gives a remainder of 1. So when I add the 2 numbers, these 2 remainders get added to give me 2. And 2 can be divided by 2. So finally, the sum will have no remainder. It will be even. So odd plus odd is even. Similarly, what about even plus even? When I add 2 even numbers, each can be given evenly to 2 people. I'll give the first number evenly to 2 people, then I'll give the second number evenly to 2 people, and I'll be left with nothing. I've added them and then I've distributed them among 2 people equally. I have no remainder. So the sum of even plus even is even. Now it's easy to conclude odd plus even. I've added odd and even. So first I take the even part and I distribute it equally. There's no remainder. Then I take the odd part and I try to distribute it equally to two people. And I know I'll get a remainder of 1 because this was odd. So finally I'm left with that remainder. So odd plus even is odd. Similarly, even plus odd is odd. How about multiplying? What about odd into even? Well, odd into even just means that I take an even number, like say 4, and I multiply it by an odd number, say 3. So say 3 into 4. So this is the same as 4 plus 4 plus 4. 3 times. Multiplication is just repeated addition. So I'm adding even numbers. And I already know when I add even numbers, the result is always even. So odd into even is even. Similarly, even into odd will be even. Because again, I'm adding even numbers. And I don't care how many times I add the even numbers, the result is always even. How about even into even? Well, again, I'm adding an even number many times, so the result is even. And lastly, how about odd into odd? Well, odd into odd had better not be even because we need some odd numbers. Odd into odd is odd. Let's see how that works. I'm taking an odd integer, say 3, and I'm multiplying it by another odd, say 5, 3 into 5. That's 3 plus 3 plus 3 plus 3 plus 3, 5 times. Now each of these numbers is odd, so each gives a remainder of 1 when divided by 2. So I'm finally left with 5 ones, which is 5, which is itself odd. So when I distribute that, I will again be left with 1 left over. So because there are odd number of remainders of 1, that sum is odd and the result is odd. Odd times odd is odd. So these are the 8 basic rules. They're not 8 different rules because the multiplication rules are just a repetition of the addition rules. Okay, so we have 5 consecutive integers. Which one of the following expressions is not odd? So I'm going to take 5 consecutive integers and test these conditions. So first I'll take the integers 0, 1, 2, 3, 4. My predisposition to 0 can be seen by one and all. I like 0 because it helps in multiplication, it helps in addition. And here they haven't said 5 consecutive positive integers, so I quickly latched on to 0. Well, this is not the only choice because here I'm starting with an even number 0. I'd also like to start with an odd number to see if something happens. So my other choice is 1, 2, 3, 4, 5. And I'm going to work these expressions with both these types. If it works for both, it's pretty much going to work for any selection because I've started with odd and I've started with even and there's no other way to start. So let's try A. A plus B plus C. That's 0 plus 1 plus 2. That is odd. What about A here? That's odd. So I don't need to try it here because they're asking which of the expressions is not odd and it is odd. So I don't need to try it. B. It should turn out to be not odd in both cases. Then I can pick that answer. If it turns out to be odd in one case, then I can't pick that answer. How about AB plus C? AB plus C is 0 into 1 plus 2. That's even. So that's a possibility. Even. Here B. 1 into 2 plus 3. 1 into 2 plus 3 is 5, which is odd. So again, B is gone because it turned out to be odd in one of the cases. How about case C? AB plus D. So that's 0 into 1 plus 3. That's odd. That's 3 odd. So we are gone. AC plus D. AC plus D. That's 0 into 2 plus 3. Well, 0 into 2 is 0 plus 3 is 3 odd. So again, we're gone. I now know that the answer is E. Let me verify it. AC plus E. AC is 0 plus E, that's 4. So 4, that's even. So we have a likely candidate. Let's try choice E with the next set of numbers. AC plus E, that's 1 into 3 plus 5, that's 3 plus 5, that's even, so not odd. So in both the cases, the fifth choice, AC plus E, gave me an even answer. So that must be the answer. That's the one that's always not odd. If n is a positive integer and n plus 1, n plus 5 is odd, then n into n plus 4 must be a multiple of which of the following? So n is positive. Remember, n is greater than 0. I can't take my beloved 0 in this case. N is a positive integer and n plus 1 into n plus 5 is odd. Let's examine this. N plus 1 into n plus 5 is odd. This is a product of two numbers and it is odd. We know the product can be odd only if both are odd. Odd and odd. That means n plus 1 is odd and n plus 5 is odd. Okay. N plus 1 is odd. So 1 less, that's n. N is 1 less, must be even. Because the odds and evens are alternating, right? 0, 1, 2, 3, 4, 5 and so on. Let's go back to the question. Look at n into n plus 4. So n into n plus 4. So n is even. Adding 4 to an even number is adding an even number to an even number. Even plus even is even. So n plus 4 is also even. So here I have a product of two even numbers. Which of the following is it divisible by? That is, must be a multiple of which of the following, which of the following is it divisible by? Okay. Now we have a product of two even numbers. We can just check what they're divisible by. Of course, the likely answer is 4 because each even number is divisible by 2. So the product will be divisible by 4. So I know the answer is 4. But here's a quick way to do it. So I want to multiply two even numbers. So the first two even numbers, I'm not allowed 0, remember, because n is positive. So 2 and n plus 4, 6. So that's 12. It's divisible by 4. Let's try the next. 4 and 8. Again, it's divisible by 12 and so on. 6 and 10, 60. It's divisible by 4. All these are divisible by 4. So we are done. The answer is B, 4. 12 is divisible by 4 and 6, but 32 is not divisible by 6. So the answer is 4. After two selections, I've got my answer. Let's move on to the next example. If x is less than y and mod x is equal to mod y, that is the absolute value of x is equal to the absolute value of y, then which of the following must be negative? Is it possible for two numbers not to be equal but their absolute values to be equal? Yes, if one is negative and the other is positive. For example, absolute value of minus 5 is 5 and the absolute value of 5 is 5. Of course, it's not possible for two positive integers which are different to have the same absolute value because their distances from 0 will be different. So x is less than y and their absolute values are equal. That means x is negative and y is the positive counterpart of x. So I can say that x is minus y. That's what I can conclude. And y is positive. For instance, 5 and minus 5. Y would be 5 and x would be minus 5. Then which of the following must be negative? Okay, so let's make our life easier. Let's just take y to be 1 and x to be minus 1. Okay, I'm going to take two choices. I'm going to take y equal to 2 and x equal to minus 2. I need at least two choices because there's some squaring happening. A, y minus x square will turn out to be 0 if y and x are 1 and minus 1. That's our first example. So it's not negative. How about x square y? Well, x square has to be positive because every number squares positive. And I know y is positive. So x square into y is positive. That rules out B. Minus xy. Well, x into y is negative because x is negative and y is positive. So minus xy is going to be positive. That rules out C. X cube y. That's interesting. X cube. Well, x is negative. So x cube is also going to be negative because it's the product of three negative numbers, which is negative. X cube y, therefore, is going to stay negative because y is positive. So x cube y is always going to be negative. The answer is D. Some more divisibility rules. Divisibility by 10 and 5. These are easy. A number is divisible by 10 if it ends in 0. Because all the multiples of 10 end in 0. 10, 20, 30, 40, 200, 1,030,000, 7,000 and so on. How about divisible by 5? Let's look at the multiples of 5. 5, 10, 15, 20, 25 and so on. The multiples of 5 move in jumps of 5. And the jumps of 5 end in 5 or 0, 5 or 0, 5 or 0. So a reasonable rule seems to be that a number is a multiple of 5 if its units place is 5 or 0. It ends in 5 or 0. Can I prove this? So let's look at a number. Say 367 and another number 365. One that is divisible, one that isn't. Again, I break it up into 300 plus 60 plus 7. 300 plus 60 plus 5. Now the 300 is divisible by 5 because 100 is. 100 is divisible by 5. The 60 is divisible by 5 because 10 is. 10 is divisible by 5. So the only thing that remains to decide the divisibility is the units place. If the units place is divisible by 5, then the number would be, otherwise it wouldn't be. So for instance, 7 is not, but 5 is. So that's the proof. All higher numbers beyond the units, the tens, the hundreds, the thousands, the 10,000s, what have you, are all divisible by 5. So the only thing remaining in this number that needs to decide the divisibility is the units place. It's exactly the same proof as divisibility by 2. How about divisibility by 3 and by 9? Okay, divisibility by 3 is much more interesting. Let's examine it in some detail. So let's look at a number, say 2461. I'm going to look at the tens place, the hundreds place, the thousands place and so on, like we were doing in the case of 2. So, is 10 divisible by 3? 10 divided by 3 gives me a remainder of 1. Therefore, 20 divided by 3 would give me a remainder of 2. 30 divided by 3 would give me a remainder of 0. 40 divided by 3 would give me a remainder of 4, which is a remainder of 1 because I further divided. So, the number in the tens place is reduced to its units. That is, if it's 60, then the remainder is 6, right? Because for each 10 in 60, I'm getting a remainder of 1. So 60 itself will give me a remainder of 6, which will finally become a remainder of 0. Similarly, 100. 100 divided by 3 gives me a remainder of 1. It's a quotient of 33 and a remainder of 1. So 100 gives me a remainder of 1. 200 would give me a remainder of 2. 300 would give me a remainder of 3, which is a remainder of 0. 400 would give me a remainder of 4, which again is a remainder of 1, and so on. So again, any 100, for instance, this 400 divided by 3 would give me a remainder of 4 first, because each 100 is giving me a remainder of 1. And then I cut down this remainder further to a remainder of 1. Similarly, the 2000. How about 1000 divided by 3? That's also a remainder of 1. It's 333 remainder 1. So you notice that any power of n divided by 3 gives a remainder of 1. And that's a beautiful property to have, because now I can break down my number again into its tens, hundreds, thousands and so on. So if I have a number 24681, I know that this 80 is going to give me a remainder of 8. I know the 600 is going to give me a remainder of 6. I know this 4000 is going to give me a remainder of 4. And I know this 20,000 is going to give me a remainder of 2. And of course, this 1 in the beginning is giving me a remainder of 1. The units can always be counted on to give themselves as a remainder. So I have all these remainders when I've divided by 3. Now I add up all the remainders. So what am I doing actually? I'm adding up all the digits. I'm just adding up 2 plus 4 plus 6 plus 8 plus 1. And then I'm dividing this by 3 and seeing the final remainder. So what's the final remainder in this case? Well, it happens to be 0, but whatever it is. So if the final remainder is 0, then the number is divisible by 3. If the final remainder is not 0, it's not divisible by 3. So all I had to do is add up all the digits and find out the remainder. And that's the age-old test for divisibility by 3, which we are all taught in quotes in school. We never taught the proof, of course, but we are told the rule. So here you have the proof of the rule. It took just about 2 minutes to prove. So let's write it down. So divisibility by 3. Add all the digits and divide by 3. Remainder 0 implies divisible. Otherwise not. Not only do you know whether it's divisible or not, even if it's not divisible, you get the remainder quickly. The remainder you get after adding the digits is the actual remainder you will get. Okay, divisible by 9. Let's see if dividing by 9 also has this great property for all powers of 10. 10 divided by 9, remainder 1. 100 divided by 9, remainder 1, because 99 is a multiple. 1000 divided by 9, remainder 1, and so on. 10 raised to n divided by 9, remainder 1. So we are set. The same logic works here. The remainder when you divide any power of 10 by 9 is 1. So any number can be broken up into its tens, its hundreds, its thousands, and each of them will give that digit as the remainder. Let's look at an example. 67042. 2 will give a remainder of 2. 40 will give a remainder of 4. 0 will give a remainder of 0. 7,000 will give a remainder of 7. And 60,000 will give a remainder of 6. Let's add up all the remainders. 7 and 6, 13, 15 and 4, 19. So final remainder is 19. I divide that by 9. I get a remainder of 1. So this number 67,042 gives a remainder of 1 when divided by 9. So it is not divisible by 9. It's exactly the same rule. Add all the digits, divide by 9, check remainder. Let's look at an example. For a 3-digit number n, PQ6. So the digits of n are P, Q and 6. The hundredths digit is P, the tens digit is Q, and the units digit is 6. Which of the following must be true for n to be divisible by 9? So we know that n equal to PQ6 is divisible by 9. By our rule for divisibility, we therefore know that P plus Q plus 6 is divisible by 9. That means the remainder is 0. Let's check all the options. P, which of the following are true? Which of the following are true? P is 3, Q is 0. So 3 plus 0 plus 6 divisible by 9. Yes. So 1 is true. What about 2? P is 3, Q is 1. That's 3 plus 1 plus 6 divisible by 9. No. So 2 is false. 3. P is 3, Q is 3. That's 3 plus 3 plus 6 divisible by 9. No. So 3 is false. So answers A, 1 only. A bank identification number consists of 10 digits with an extra 11th digit called the check digit. So there are 10 digits and an 11th check digit. We have 10 digits. The check digit is the remainder when the 10-digit number is divided by 9. So you divide this number by 9 and this is the remainder. This is done to check if an identification number has been wrongly entered into the computer. Which of the following is the correct identification number? So I'll have to divide the first 10 digits, that number, by 9 and check if I get that remainder. Let's quickly do it for A. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. And I get a remainder of 1. Do I? So 9 gives me a remainder of 0. 8 and 7, 15. 15 plus 3, 18. So these three go. They give me a remainder of 0. 5 plus 4, 9. They give me a remainder of 0. 6, 2, 1 add up to 9. They give me a remainder of 0. So totally the remainder is 0. A is out. Let me check B. 3, 2, 1. 3, 2, 0. 1, 7, 6, 4. I want a remainder of 5. So I'm grouping in 9s because 6 plus 3 is 9. That gives a remainder of 0. 6 plus 3. 7 and 2 gives a remainder of 0. 4, 5, 6, 7, 8, 9. 4, 5, 6, 7, 8, 9 gives a remainder of 0. What's left is 1 and 1, 2. So the remainder is 2. B is out. Let me check C. 2, 5, 7, 0, 9, 3. 6, 2, 8, 3 and a remainder of 0. 9, I love 9s. That's gone. 7 and 2 gone. 6 and 3 gone. 5, 6, 7. 7 and 8. 15 plus 3, 18. 18 is divisible by 2. So all gone and the remainder is 0. This number gives a remainder of 0. The answer is C. More divisibility rules. Divisibility by 4 and by 8. Recall the divisibility rule for 2. The tens, hundreds, thousands and so on, all the higher order digits were divisible by 2 because 10 is divisible by 2, 100 is divisible by 2 and so on. So the only deciding digit was the units digit. That decided whether the total number was divisible by 2 or not. I'm going to try the same thing for divisibility by 4. So is 10 divisible by 4? No. Is 100 divisible by 4? Yes. Is 1000 divisible by 4? Yes, of course, because 1000 is a multiple of 100 and 100 is itself divisible by 4. And so on. So 100 onwards, all powers of n greater than equal to 2. 100 onwards, all powers of 10 are divisible by 4. That is, it's only the tens and units place of the number that actually decide divisibility by 4. The hundreds place onwards are always divisible by 4. So the rule is simple. I take the whole number and then I just look at the tens and units place and look at that number. Is that number divisible by 4? If yes, then this whole number is divisible by 4. Let's elaborate with an example. 3, 2, 6, 0, 4, 8, 2. So I know 100 onwards, this number, what do I mean by this number? 3, 2, 6, 0, 4, 0, 0. This number is divisible by 4. What's left is the number 82. Because these two add up to the whole number. So 3, 2, 6, 0, 4, 0, 0 is divisible by 4 because it's a multiple of 100. So I only need to check if 82 is divisible by 4. So I just look at the tens and the units place of the number and check if it's divisible by 4. This gives a remainder of 2. So it's not divisible by 4. Same thing for divisibility by 8. I need to find out the first power of 10 that is divisible by 8. Well, 100 is not divisible by 8. The remainder is 4. But 1000 is divisible by 8. The remainder is 0. The quotient being 125. So 1000 onwards, all powers of 10, remainder 0 for n greater than equal to 3. All powers of 10 greater than 1000 will be divisible by 8. So just the first three digits, the hundreds, tens and units will decide divisibility. So if I want to check divisibility by 8, I just look at the first three digits of the number, look at that number, it's a number in the hundreds, and check for divisibility by 8 for that number. Again, let's look at an example. 6, 4, 8, 9, 0, 0, 3, 2, 4. This number can be written as 6, 4, 8, 9, 0, 0, 0, 0, 0, plus 3, 2, 4. This part of the number is divisible by 8 because it's a multiple of 1000. And 1000 is divisible by 8. Contains 3 zeros. So all that's left to check is whether 324 is divisible by 8. So that's an easy enough division. 324 divisible by 8. No, because 320 is divisible by 8, I know. So the remainder will be 4. So this whole number is not divisible by 8. Its remainder is 4. So the rules for 4 and 8 are covered. Actually, the rules for 2, 4 and 8 are all similar. Rule for 2, only look at the units place. Rule for 4, look at the number in the tens and units place. That 2-digit number. Rule for 8, look at the number in the first 3 digits, the hundreds, tens and units place. That 3-digit number is divisible by 8. The rule for 16 will be identical. The rule for 32, the rule for 64, the rule for any power of 2 will be the same. If you want the rule for 32, 32 is 2 raised to 5. So I'll look at the first 5 digits of the number and check whether that is divisible by 32. Of course, that's a massive pain to do. So we don't really glorify this rule. It only makes practical sense up to 8 or 16. But the proof goes through. Any power of 2, if you want to check if a number is divisible by that power of 2, just look at those many digits. Which of the following numbers is divisible by 4 but not by 8? Divisible by 4, I need to look at the first 2 digits and look at that number. 22, not divisible by 4, remainder 2. So that option is gone. 24, yes, divisible by 4, remainder 0. But is it divisible by 8? To check divisible by 8, I have to look at 3 digits, 0, 2, 4. Yes, remainder 0 even when divided by 8. By 4 the remainder is 0. By 8 the remainder is 0. So the answer is B. Let's just check let's just practice the rule on C. Divisible by 4, look at 72. Remainder 0. Yes, it is divisible by 4. Look at the 3-digit number, 372. Is it divisible by 8? 320 is divisible by 8. So I have 52 left, 48 is it, so remainder is 4. So C is not true because, so C is, I'm sorry, what am I doing? B is not true because B is divisible by 4 and 8. Here we found C, that's the answer. It's divisible by 4 but not by 8. So C is the answer. I'm in too much of a hurry. I didn't read the question properly.